If viruses are smaller than the wavelength of visible light, which most are, why can't we just use shorter wavelength light, aka electromagnetic waves, and then just techno-shift it to what our puny human eyes can see? Sort of like what infrared night vision goggles do. Everybody do the techno-shift. There are two big reasons for it, and I think it's related to why we didn't evolve to see smaller wavelength light in the first place. But there's also a super cool workaround that scientists have developed. In a microscope, it's like shining a flashlight through a small object where some light gets absorbed and some passes through, and then using magnifying glasses on the other end to blow the image up. But to understand the effect of wavelength, think of it like one of those old pin art toys, where the wavelength is roughly like the size of those pins. If the pins are very thick and you press it against your face, you lose any details much smaller than the pin size. But when the pins are smaller than the features, you get a good image. So why not use the tiny UV or X-ray pins? I'm glad you asked. The first problem is, the shorter the wavelength, the higher the energy. So the first issue with using the UV or X-ray pins is that it's like taking that pin toy and slamming it against your face instead of pressing gently. It could destroy the tiny structures you're trying to image. The second problem is the lenses. Visible light passes through glass while bending a bit, so we can use glass lenses to focus and expand the beam. But for shorter wavelength UV light, glass acts more like a wall. Fun fact, this is why it's hard to get a sunburn through glass, because glass blocks most of UVB light. These problems are not insurmountable. There are UV microscopes that use funky crystal lenses and mirrors, and even X-ray microscopes that use fancy math to image all the way down to 10 nanometers. But they're limited, especially when dealing with biological material. Enter the electron microscope. Instead of electromagnetic waves, the flashlight fires a beam of tiny particles that acts partially like tiny particles and partially like waves. But they're charged particles, so we can use electromagnets as lenses. And in the beam, their wavelength can get below 0.1 nanometers, which is roughly the size of an atom. Imagine you have a tiny Lego ship inside of a dark room. You can't see it directly, so you fire an extremely fine stream of microscopic sand at it. Some grains pass through, some bounce away, some get blocked, and some scatter at weird angles. A detector on the other side records the pattern. Then a computer says, based on how the sand scattered, here's the shape that must have been there. That's electron microscopy, which got the Nobel Prize for being developed back in 1986. But then in 2017, there was another Nobel granted for cryo-electron microscopy, which adds one more step.
Those LEGO spaceships are frozen in clear glassy ice first,
Letting scientists take thousands or millions of electron shadows from different particles, so it doesn't wiggle, collapse, or dry out, and use math to reconstruct them all into a 3D model. Like this virus. Isn't science so cool?